Hey everyone, and welcome. Today we're tackling a Leetcode problem called candy. It sounds sweet, but it's got a bit of a tricky logic to it. Don't worry, we'll break it down step by step, making it super clear. Ready? Let's dive in. So here's the setup. Imagine a line of children, and each child has a rating. Our job is to give out candies to these children. There are two main rules we absolutely have to follow. First, every single child must get at least one candy. No child gets left out. Second, if a child has a higher rating than one of their immediate neighbors, the person to their left or right, they must get more candies than that neighbor. Our ultimate goal is to find the minimum total number of candies we need to distribute while satisfying these two conditions. We're given the ratings as a list of numbers. The constraints tell us the number of children can be up to 20,000, and ratings are positive numbers, also up to 20,000. This means a very slow solution, probably won't pass. Okay, let's look at the first example. The ratings are 1, 0, and 2. The problem states the output is 5 candies, distributed as 2 for the first child, 1 for the second, and 2 for the third. How do we arrive at this? Let's think about the rules. Everyone gets at least one candy. So a naive start might be to give everyone one candy. So the list of candies would be 1, 1, 1. Now, the first child has rating 1, second has rating 0. The first child doesn't have a higher rating than the second, and the second child doesn't have a higher rating than the first. The second child has rating 0, and the third child has rating 2. Here, the third child's rating is higher, so the third child must get more candies than the second. If the second child has 1 candy, the third child must get at least 1 plus 1, so 2 candies. Our candies might now look like 1, 1, 2. But what about the first child compared to the second? The first child, rating 1, has a higher rating than the second, rating 0. So the first child must get more candies than the second. If the second child has 1 candy, the first must get at least 2. So this updates our candies to 2, 1, 2. This gives a total of 2 plus 1 plus 2, which is 5. This matches the example. For the second example, ratings are 1, 2, 2. The output is 4 candies. 1, 2, 1. Again, start with 1, 1, 1. First child, rating 1. Second child, rating 2. Second is higher, so second gets more than first. If first has 1, second gets 2. Candies, 1, 2, 1. Second child, rating 2. Third child, rating 2. Their ratings are equal, so this rule doesn't force one to have more than the other. The third child can keep 1 candy, so 1, 2, 1 works. Total is 4. These examples hint that we need to consider neighbors carefully. So, what's our first instinct? Well, we could try to list out every possible way to give candies, and then pick the smallest total that fits the rules. But with up to 20,000 children, that's just not going to work. It would be astronomically slow. This kind of problem, where we're trying to find a minimum and make local decisions, often points towards a greedy approach. That means we try to make the best local choice at each step, hoping it leads to a global optimum. Let's refine that greedy idea. The tricky part is that a child's candy count depends on both their left and right neighbors. If we only look left, we might mess up the right side condition, and vice versa. A common strategy for this kind of problem is to use 2 passes. First, we can iterate through the children from left to right, ensuring the rule about the left neighbor is satisfied. Then, we can iterate from right to left, ensuring the rule about the right neighbor is satisfied, without undoing the good work from the first pass. Here's how the 2-pass logic works more concretely. First, we give every child 1 candy. This handles the at least 1 candy rule. Then, for the first pass we go from left to right. For each child, if their rating is higher than the child to their left, we make sure they get 1 more candy than that left neighbor. After this pass, all left neighbor conditions are met. For the second pass we go from right to left. For each child, if their rating is higher than the child to their right, they must get at least 1 more candy than that right neighbor. Crucially, we take the maximum of what they currently have from the first pass, and this new requirement. This ensures we don't accidentally reduce candies if the left to right pass already gave them more. Alright, here's the Python code that implements this 2-pass idea. It might look like a bit at first glance, but don't worry. We'll walk through each part so it makes perfect sense. The core logic directly follows what we just discussed. First up, we get the number of children, let's call it N, from the length of the input ratings list. If there are no children, we just return 0 candies. Then, this is important, we create a new list, let's call it candies, that's the same size as the number of children. And we fill it with ones. This immediately satisfies that first rule. Every child gets at least 1 candy. Now for the first pass. We loop through the children starting from the second child, at index 1, all the way to the last child. Inside the loop, for each child, we look at their rating and compare it to the rating of the child to their immediate left, at index I-1. If the current child's rating is greater than their left neighbor's rating, then we update the current child's candy count. They get 1 more candy than whatever their left neighbor has, so candies becomes candies, 1 plus 1. Next is the second pass. This time, we loop from right to left. We start from the second to last child, at index n-2, and go all the way down to the first child, at index 0. For each child, we compare their rating with the rating of the child to their immediate right, at index I plus 1. If the current child's rating is greater than their right neighbor's rating, they need more candies than that right neighbor. Specifically, they need at least the right neighbor's candies plus 1. But remember, the current child might already have a certain number of candies from the first pass. So we take the maximum, either what they currently have, or what their right neighbor has plus 1. This ensures we satisfy the right neighbor condition, without accidentally reducing candies they deserve from the left neighbor condition. Finally, after both passes, our candies list has the minimum number of candies for each child that satisfies all the rules. All we need to do now is add up all the values in this candies list to get the grand total. We initialize a total candies variable to 0, loop through our candies list, add each child's candy count to the total, and then return that total. And that's our answer. So how efficient is this 2-pass solution? For time complexity, we make 1 pass from left to right through the n children, and another pass from right to left. Each pass takes a number of steps proportional to n. So the total time is big O of n, or order n, where n is the number of children. This is really good and should pass easily. For space complexity, we create an extra list, the candies list, which is the same size as the input ratings list. So we use extra space proportional to number of TIS. This is called big O of n, or order n space. So to wrap it all up, the candy problem asks us to give out the minimum number of candies while making sure everyone gets at least 1, and kids with higher ratings get more than their lower-rated neighbors. The brute force way is too slow. The clever trick is the 2-pass greedy strategy. First, we ensure everyone has 1 candy. Then, a left-to-right pass handles the more-than-left neighbor rule. After that, a right-to-left pass handles the more-than-right neighbor rule, using a max function to make sure we don't undo the work of the first pass. This approach gets us the minimum total candies efficiently, in what we call order n time and order n space. Pretty neat, huh? Hope that breakdown made the candy problem a lot clearer. If this explanation helped you out, I'd really appreciate it if you hit the like button. Consider subscribing for more Leetcode explanations, and if you have any questions or other ways to solve it, drop a comment below. And hey, if you're feeling extra generous and want to support these tutorials, you can always contribute to the Boba Fund. Keep practicing, keep coding, and I'll catch you in the next video.